Let's now consider this confidence interval problem. We have a sample of 680 households from a very large city, and the average number of TV sets works out to be 1.86, with a standard deviation of 0.8 in the sample. To find a 95% confidence interval for the average number of TV sets in the city. First off, we notice that this is a sample that is drawn without replacement, but it's from a really big city, and so essentially it's with replacement. There's very little chance of drawing the same household twice to count the number of TV sets. And so we will use the formula as if it was with replacement and ignore the finite population correction factor. So what we have here is the sample average of 1.86, and so our confidence interval will be centered on that sample average of 1.86. That's our best guess for the average for the city. Now clearly that's not exactly correct, but it is our best guess, so 1.86, then plus or minus some tolerance, plus or minus a standard error. Now the size of the standard error is going to be equal to a number off the z distribution, alpha over 2, times the sample standard deviation divided by the square root of n. A comment here, we use the bell curve because I have a large sample, 680, and so the bell curve will apply. It will be a very accurate approximation. So we have the bell curve, and we need to find the number so that 95% of the area lies in the middle, so that 5% lies in the tails combined, or that 2.5% lies in the upper tail. So that's the meaning of the z alpha over 2, that if here my alpha is 5%, and so alpha over 2, the area to the right here is going to be 2.5%, so that 95% lies in the middle. And by now this is our old friend, 1.95996. And that's our value of z sub 0.025. Okay, so we've got everything we need now to construct the confidence interval. So 1.86 plus or minus 1.95996 times s, which is our sample standard deviation of 0.8, divided by the size of the sample, which was square root of 680. And so we get 1.86 plus or minus, and then we plug into the calculator. To get our standard error of 0.006, or 0.06, pardon me, 0.06, and then it's 0.1 after that, so we'll just leave it as 1.86 plus or minus 0.06. So that is our 95% confidence interval for the population mean, the average number of TV sets for all households. Let me run through some of the misinterpretations of this. Clearly, that is not the we're not saying that 95% of households have between 1.8 and 1.92 television sets. That's patently absurd. We're also not saying that there's a 95% chance that the average is between 1.8 and 1.92. The population mean is some number, we just don't know what it is. So it doesn't make sense to say that there's a 95% chance that it's in this range. Either it's in the range or it isn't in the range. The population mean is some constant that doesn't change. Our interpretation of the confidence interval is as follows. If we have, say, 100 people do their own confidence intervals, take their own surveys of size 680, and we have 100 different confidence intervals that are made based on these different surveys, 95 of these people will get the get it right. 95 of them will have a confidence interval that covers the true mean, and 5% will get it wrong. The 5% that get it wrong wouldn't necessarily have done anything wrong, they just simply have bad luck that the population mean is not in their intervals. So that is our interpretation of a confidence interval. That if 100 people did a survey like this and get 100 different confidence intervals, 95 of these confidence intervals would be correct, 5% of the confidence intervals would not cover the true population mean. We use the bell curve because we have a large number of samples, a large sample size, 680. The sample standard deviation can be replace the population standard deviation. Technically, it should be sigma, where I have an s over square root of n, where there's an s over square root of n. Technically, that should be sigma divided by square root of n. However, because I have a large sample, replacing sigma by s is completely reasonable. And another comment is that there is no such thing as a 100% confidence interval. I can't have a confidence interval where I'm 100% certain, guaranteed, that I'm covering the true population mean, because the bell curve here stretches out to infinity, so I can never go so far out to the left and right to be 100% certain that I've covered all of the covered all the area. There's always going to be area to the extreme far left and to the extreme far right, no matter where I make the cutoffs.